This is our second video on gases. We're going to start talking about the gas laws and using kinetic molecular theory to explain them. I want you to take a look at the top of the note packet on page 188 where it says common misconception. It's a box, it should be in gray, and it says in all gas law calculations temperature units must be expressed in Kelvin. And so you have several of these boxes that say common misconception in your notes, and I want to point out that the text in these boxes is actually telling you what's correct. What they're writing about is not the misconception, they're writing about the correction to the misconception. So in this case, it's telling you that when we use gas laws, we're going to have to express temperature in Kelvin, and any temperature in Kelvin is equal to the degree in Celsius plus 273. You need to remember that, and that's important because if we use Celsius, we would be using a negative number sometimes in gas laws, and you can't have a negative pressure. So kinetic molecular theory helps us understand how the pressure of a gas will change when the volume changes. We learned previously that when pressure goes up, volume goes down, or when pressure goes down, volume goes up. We learned that pressure and volume are, we called it inversely proportional. This was last year. But we can use, that word is proportional. We can use kinetic molecular theory to explain why this is. So if we have a container that contains some gas, and those gas molecules are moving around, they're all moving pretty rapidly, the molecules are far apart, there are no attractions to them, they're always moving, they're creating pressure by hitting the sides of the container. If we make the space, if we push the top down and make the space smaller, you're going to have the same number of particles in there, they'll be moving at the same speed, but they will be hitting the sides of the container more often because the container got smaller. So that is why if you decrease the volume, the pressure increases. I'll say that again the way it says it in your notes. When the volume of a container decreases, the molecular collisions, that's these little molecules bumping against the wall, occur on a smaller surface area because you have decreased the surface area. And since pressure equals force over area, if the area gets smaller, then the pressure will get greater. We call this relationship that I'll circle in green, we call it Boyle's law because it was, I believe, discovered or published by Boyle, or somebody gives him credit. And the way we write it is pressure times volume, first pressure times first volume, which you could say that would be the pressure in this container, the pressure in the volume. That is equal to the second pressure times the second volume. And we call this Boyle's law, and we use this in math, in applied math problems. So the second pressure in the second volume you could think of as the pressure and volume of this container. We can use Boyle's law to think about what things that happen in the atmosphere. If we have a balloon here down on ground level and we let it up and it flies up into the atmosphere, the pressure up, the higher you go in the atmosphere, the pressure decreases because you actually have less air up there. Down here at ground level, you have lots of air molecules. So you have lots of air I'm drawing little dots to represent a lot of air molecules, and they're all air molecules are oxygen, nitrogen, and carbon dioxide molecules, and they're all moving around and hitting things and creating pressure. But the higher up in the air you go, you have fewer of them. So if you have fewer molecules, you have fewer collisions, less pressure. So there's less pressure up here, and with less pressure surrounding the balloon then can expand in size because there's less pressure holding that balloon down. Here there's the more weight of air, so there's more pressure that's holding it down. The amount of molecules inside the balloon doesn't change. You still have the same number. It's just that there's less force on the outside, which is why the balloon can expand as it goes up. Now, it's important when we think about pressure problems that we define our systems carefully. Over here, when we were looking at our containers, they had rigid walls. So when we push this top down, we made the volume smaller, and therefore these gas particles inside, there were the same number of them moving at the same speed, and they created greater pressure on the inside. A balloon is a little different, because a balloon has a flexible membrane. So this is flexible here. So when you blow up a balloon, the pressure inside the balloon is going to be equal to the pressure outside the balloon, because if it wasn't, the balloon would continue expanding until the pressure inside the balloon equals the pressure outside the balloon. So it's just something to think about when you think about things with a flexible outer coating. Before we move on to doing some practice problems, let's just remember what a graph of pressure and volume looks like. So if you take volume, this is how it looks in your notes, and pressure here, and you graph pressure and volume, whenever you graph an inversely proportional relationship, that graph looks like this shape. So that is what the graph of an inversely proportional relationship. If you take math, you can tell me what that's called. I can't remember if it's a hyperbola or what it's called, but anyway, that type of curve is what an inversely proportional relationship looks like when it's graphed. So here you have a sample problem, and you want to solve it. It says, what if a pressure of a fixed amount of gas doubles at constant temperature, what happens to its volume? So how would we go up? There's several ways to think about solving this problem. We could say, okay, well, we're talking about pressure of a fixed amount of gas, and they're asking about volume, and they tell us that temperature is constant, so I'm not going to worry about temperature. And I know, so if I looked at that and said, well, I'm thinking about pressure and volume, I would write down one thing I know about pressure and volume is that P1V1 equals P2V2. So maybe, I would say to myself, maybe I can use this to solve this problem. I look back at the problem like, oh, but I have no numbers. So what would I plug in? Well, let's see if, even though we don't have numbers, if we can use relationships. So it tells us the pressure of a fixed amount of gas doubles. So that means if P1 equals X, then P2 equals 2X. And it's asking what happens to the volume. So that means V1 would equal Y, and V2 is what we're trying to solve, which we'll just call question mark right now. So let's plug in these variables. So we have X times Y equals 2X. I'm putting 2X for P2 times question mark, which I'll put in parentheses. So let's see if there's a way we can simplify this. Well, I want to get question mark alone because that's what I'm trying to solve for. I probably should have not called it question mark. But if I want to get it alone, I'm going to divide both sides by 2X. So I divide both sides by 2X. On this side, this cancels. Over here, the X cancels. And now I'm going to write this in a different color. So now I have Y over 2 equals question mark. So that essentially gives me my answer. If my initial volume was Y, then now I know that my final volume, which is question mark, is going to be Y over 2, which I could rewrite as initial volume over 2, which is 1/2 times my initial volume. So what would happen to its volume? I could write the answer. So then you could write as the answer, the volume would be cut in half or divided by 2. You could also take a more conceptual approach to this problem because we know you could start out by reading, if the pressure of a fixed amount of gas doubles at constant temperature, what happens to the volume? You know you're thinking about pressure and volume and that temperature is constant. And you know that pressure and volume are inversely related. So if pressure goes up, volume goes down. And pressure is going up here. They're not just inversely related, they are proportional. Pressure is proportional to volume. So to the extent that pressure goes up, volume will go down by that same extent, by that same ratio. So if pressure doubles, that means volume will be cut in half. If pressure triples, that means volume will be cut by 3. That's what this proportional sign means. They have the, however much volume is multiplied by, however much pressure is multiplied by, volume will be divided by that much. So if pressure is doubled, which we wrote right here, that means volume has to be divided by 2. So that'd be a more conceptual approach to answering this question. Your answer will be the same.